All right. Hello everyone. Welcome to the very last theory track workshop. And today's topic is modern deep learning. You may be like, this sounds vague. What in the world does modern deep learning even mean in the first place, right? So basically what this is we're kind of giving you four separate topics, which are all kind of snippets of what we have done in our biweekly reading group. And you will see, a little bit more info about that as well. Any coming times. And it gives a little flavor of what we do in our reading groups, the things we talk about. And if you're interested, every single one of these, at the end, we also have a recording of our past reading group. And in the future, it is very likely that one of our officers will also revamp that and give it as another reading group as well. So if you like the sort of things that we're talking about here, reading group will be a great place to go. So yeah, before we start, a few announcements. Speaking of reading group, first of all, we have the last one for this quarter coming up this weekend. And this one is going to be given by Kevin Wang, and the topic is going to be on neural AI, specifically from statistical physics to neural computation, the underlying geometry of why intelligent systems work. So this one's going to be a bit more of a meta one, if you will. It looks at the intersection of neuroscience and machine learning, and it looks at the patterns between those and tries to of them doing the classification task and asking the question of what exactly about our brain and what exactly about these neural networks makes it that it looks like it has intelligence. So it is a very interesting reading group that's happening this Saturday, 12 to 2 p.m. at Engineering 6 289. And another thing is, this is the last workshop, and next Monday, this time at Kinsey Pavilion 1240B, we're going to have the ACM AI X Cyber Winter Symposium. So we have this every quarter. This will be the third quarter we're having this now. There will be free food, which is always fun. But basically, it is a little event where everyone in AI and everyone in cyber, mainly the projects people, will kind of come out and just present what we have been doing for this entire quarter. Some professors and grad students will be there, and it will just be overall fun time. We can hang out with a lot of people and just talk about what we have done. For those of you who are in workshops right now, you'll be in projects next quarter, so you can get a glimpse at what you may be doing in the future. And best of all, if you RSVP in this link, we will have free dinner. There will be pizza and there will be boba. So Thai tea. So that's pretty good. So you can come to that if you want. It is always like this big event where we have 100+ attendance and you get to see everyone in the club. So I think it's always really fun. And yeah, looking at a roadmap, we are actually, as I was saying, at the very, very last workshop, we were at modern deep learning. So I just want you guys to stare at this for a little bit, and it's we did all of this, right? This entire quarter, and you should be very proud that you have done this. Okay, the Regate recording has not gone up yet. I will post that soon. But yeah, we have covered a lot, and this will kind of wrap up everything and kind of give a sort of here's how deep learning, cutting edge deep learning research is being sort of implemented and being used in today's research. So yeah, a bit of overview of what we're going to talk about today, the four big topics. The first one is mobile nets and other efficient networks. So this looks at the question of, hey, if you want to put these huge models and want to run them on, say, mobile devices or other, low power devices, how do you do that? What do you do to networks to be able to make that happen? The second one is the landscape of generative vision, which basically talks about what is generative vision. You see AIR floating around. What is that? How does that actually work? And we talk about architectures before, like VAEs and GANs, and those GANs, which you will be working with in Products Track, and also today's quote-unquote state-of-the-art, which is diffusion models and stable diffusion, which you may have heard of. And number 3 is introduction to reinforcement learning, which is a almost generalization of what we have learned so far with a lot of machine learning, and asks, what if our data set is changing as we're training? And what if we can't backpropagate through our loss function? What happens in that? How do we train a model in that way? And that's actually how a lot of self-driving cars and a lot of game AI agents is trained, and also how ChatGPT is so good. And number 4, advanced large language models, which is kind of a continuation of what we had in week 5. As you can see over here with, intro to LLMs, where our team will just kind of give us the sort of today's state of the art of large language models and what they are, stuff like that. So without further ado, let's get started with mobile nets and other efficient networks.
Okay. So far we've talked about a whole bunch of stuff, but you might notice a problem with a few of the architectures we talked about, especially the more sophisticated ones, which is that there is a problem with how much memory is being used, right? So if you have really sophisticated equipment like GPUs that are super fancy and stuff, this is not as much of a problem. But if you want to run it on something that's more accessible, like a phone or some kind of device or whatever, or some kind of laptop or whatever, that's a little bit more difficult to make it full because you just don't have the memory to do the things you need to do. So in order to sort of solve this problem, the concept of efficient nets was sort of created. So to sort of delve further into what exactly the nature of this issue is, we can sort of separate this out into three components. Firstly is, of course, the actual memory storage that I alluded to earlier, which is that there's a whole bunch of parameters that we need to learn. And so you need to have significant storage space for dealing with these parameters, for updating them, for figuring out gradients and so on. And there's also a high energy consumption because you need a lot of GPUs running in parallel for extended periods, days, weeks, and that ends up leading to substantial energy use because the more GPUs you have running, the more power they need to draw. And like over time, this can be a very, very significant source of carbon emissions, which obviously is not a good thing, especially as AI becomes more and more powerful and more prominent. And then the third problem is that the core of the neural network operations, like the matrix operation and so on, that requires the high computational abilities of GPUs, but even like the number of operations that are being done is so high that it strains even like what GPUs are able to do. So that's sort of like the three-part, those are like sort of the three parts of like the memory issue when it comes to neural networks as they are today. So as you will recall, way back in week 2, we talked about convolutional neural networks as a way to sort of ease up the memory issue that we found with feed-forward neural networks. Right, where instead of having like a giant flattened layer of an image that then just like goes to a next layer and so on, which leads to a lot of weights that need to be learned, instead you can use filters and run those over it through convolutional layers, and that ends up leading to less parameters that need to be learned. So there's sort of a similar like problem there, and you'll see that the issue that we're solving has a similar solution as well with efficient nets. So the way that you have with convolutions, right, with normally what you're going to have is you're going to have filters that are going to be running over input data that's going to be leading to outputs. So each filter you can think of as being like one element, and you're going to have m filters that are running over them, and you run that over the entire data. So it's going to lead to n times d squared dp squared, which is here, times dk squared, which is here, times m multiplications. So this is dk, this is dp, this is df, because we need to have that many outputs to deal with. Okay. So the solution with efficient nets is that you sort of have to decrease this number of multiplications for like normal convolutions, just as we did for convolutions relative to feed-forward neural networks. And so in this case, what we do in order to minimize the number of multiplications we need to do to get to the answer is that we sort of split up our task into two parts, a depth-wise convolution and a point-wise convolution. Okay. So normally what we find with convolution operations, right, is that we have to, normally with convolution operations, what we need to do is that we have to transform it like n times if we have n filters. However, what we do with the separable convolutions is we end up only needing to do it once. And so that way we save up a lot of memory storage in that respect because we only need to do it once as opposed to doing it n times. Here we go. So you can see that there's a very strong difference between this value and this value because on the order of like d squared m versus d squared times n. So which means no matter how many filters we add, that's only going to result in some constant being added as opposed to multiply. So that reduces the time complexity and just overall the memory complexity like quite significantly by the order of like a whole variable. So where this goes in relation to this dk squared as opposed to dk squared n. And again, just to go back through these separable convolutions is, again, we're splitting it into a depth-wise convolution and a point-wise convolution. Okay, perfect. So there's an architecture called MobileNet that sort of utilizes these insights in order to create something that's more efficient, that uses up less memory, and thus it saves up on energy and time costs, which you can see here. And you can also see that it matches the accuracy of like other state-of-the-art models, but that aren't quite so efficient. So you can see that this is in fact a fairly good way of like trying to save up on these sorts of costs that we discussed at the beginning of today. Another way that we can save up on memory is that we just change the number of bits that we need to store values. So normally we have 32-bit floats, right? But if we, instead of using 32 bits, we use 8-bit integers, then we'll end up sort of representing the same values, but we'll require fewer bits to do so. And this will result in reduced accuracy because we're no longer able to encode as fine values, given that we just have fewer bits for resolution. But while that could lead to a loss in optimality, overall it takes less memory to train a network this way. So you can see that you would have 128 megabytes of storage if you have 20 million weights and 16 million activations. So that's like quite a bit that we can save by reducing the precision just a little bit. And one added benefit with the precision is that it introduces nonlinearities. So we can use that as part of our activations as well. So while the resulting loss in precision does sometimes lead to loss in optimality, we can also leverage that for other uses as well. Perfect. So yet another example of efficiency is that really, I guess, since neural networks are inspired sort of a little bit by how actual neurons fire, we can also like take an inspiration from like how the human brain sort of optimizes power and sort of apply those same insights to computing as well. And this would like lead to, this would be more on the hardware side, where we create basically things called neuromorphic chips, which you take basically achieve brain-like efficiency a little bit more or less. And so you can see that we have innovations both on the architecture side, where we come up with sort of more efficient ways to do the multiplications and the convolutions, and we also have advancements on the hardware side with things like neuromorphic chips. And together, both of those end up leading to better results for like memory capacity, which we would like to use less of, and also energy usage, which, as you can see with these neuromorphic chips, it helps quite significantly with that. Okay. So I'll just like let you look at this diagram for like a couple seconds. And
so also, quick thing I want to mention is if we were to go back to the like definitely separable convolution and the mobile net stuff, you may be like, how is this useful? Right? Like, yes, now we can run like with classification models on phones, but like, why doing this? We could retrain this anyway. Fun fact: last quarter for our competitions track, the thing that we did over our projects was, if I remember correctly, some sort of we were doing RNA classification, and the specific thing about that challenge is we were supposed to be able to have it run on a CPU, like the resulting model run on a CPU within 1 to 2 hours for the final inference. So what we did, our competitions team did, is basically took mobile nets and then used that architecture as a basis to then start to train different models. And another intuition of like you may think of why this would be good is with a normal convolutional neural network. Oh, this doesn't work. With a normal convolutional neural network, let's hope any of these markers will work. There we go. With a normal convolutional neural network, if you were to look at the channel dimension, we have what is basically a dense network, right? Every single layer is connected to every single other layer, and it's really, really dense, and we have usually a pretty large number of filters, 3 by 3. This is what a normal network looks like, which is like, that's fine, but you can see how that can add up really quickly. Even though, for convolutional filters themselves, they're 3 by 3, it is still dense in the channel dimension. Every channel's 3 by 3 filter will output to every other channel's 3 by 3 filter, and you're gonna have separate filters for all of these, and you're gonna have that for every single input filter, and because of that reason, or input channel, and because of that reason, it can get really big really quickly. If we were to try to visualize what mobile nets are doing, specifically with depth-wise separable convolution, is with a single one, we split it into two separate operations. The first operation is depth-wise, so we kind of do something like this instead, or like specifically like that. It's a depth-wise convolution. It looks something like this, right? And basically, because we're doing this instead of having a dense convolution, this is much smaller because this grows linearly at a size of n instead of the size of n squared. Because before we would have every single thing connected to every other thing. Now we just kind of like have this pair of connections. And then you may be like, okay, we have this connected, so this is kind of like our channel dimension. But the channels aren't communicating with each other, right? So we may have like a 3x3 filter here. Then we have our dense connection on the second layer, which is our separate pointwise convolution. In this case, we only use a 1x1 convolution. So that's 9 times the size of what it was before. And this is also much smaller because it grows as linearly instead of, at polynomial or n squared. So that's much smaller at the end. So basically we're kind of saying, when we have a convolutional neural network, let's first do our filter dragging, where we look at the spatial dimension. And then our pointwise operation, then let's look at the channel-wise dimension. So we're kind of doing, let's mix everything around spatially, then let's mix everything around channel-wise. So we're kind of separating that, and you may be like, yeah, that's less parameters, so that means it's going to be a worse model. And like, yes, it is physically not as able to mix the information and be able to, kind of add the information together as much as a normal convolutional layer would. But the great thing about gradient descent is if you do it for long enough, generally speaking, as long as your network is big enough, it's going to work, right? So in short, because of this, this works really well because this works really well because we're able to train the network to be able to adapt to this. So the network is always forced to extract more information at a time. Does that kind of make sense? Okay. Any questions before we move on?
So does that mean you're not mixing information between the channels as much?
You can make that argument. So like, it's not necessarily you're not mixing information between the channel as much. It's more of saying you cannot mix information between the channel and the spatial dimension simultaneously, which may lead to some problems because kind of what you have to do is say, I have a, let's say I have a pixel here that I want to like, it's information, I want to move over here. Then I want to move it along the channel some number, right? When I just do a normal convolution, the filter can just move it and it can just move it to some other channel and we're good. But the thing is, with this one, what the filter has to do is first move it to that location. That's a new layer, and then take that and then move that to the new channel. So because that intermediate step right there, it is slightly less flexible because you can't like swap things around as freely as you can, like intuitively speaking. But because again, like all this, like the network is trained so that it will be optimized to this architecture specifically, because that's what gradient descent is. So in the end, what we have found, at least empirically, is that it works good enough. Is that gonna make sense? Yeah. And I also want to emphasize that this really only works, at least what we have found so far, for classification networks, where the outputs are simple-ish. Like it's like, like a 10-dimensional vector or a 100-dimensional vector. But like personally, like in the past, I've tried to train like diffusion models and other generative models based on these architectures, and generally they fare a lot worse. Like they work if you like train it for long enough, but you start to see some downfalls of not having this flexibility to be able to switch things around nearly as much. The great thing about classification is because the outputs are so simple, which is a 10-dimensional vector, it is really easy for a network to go, okay, I gotta do something to my inputs, compress it down so that, in my output, it's just a 10-dimensional vector. But it's much harder for it to say, okay, my output has to be the same dimension as my input or something like that. It becomes a lot more difficult. So in classification and other tasks where we can, what we call where the model can really almost like overfit to what the output's supposed to look like, it's kind of works a lot better. If that makes sense.
Yeah.
Yes. Yeah. That by separate convolution. I know you joined late, so that's totally fine. But basically, with normal, a really quick summary, with normal convolutions, it's just like, you have a bunch of filters. Each input channel maps to each output channel, and it's like an n squared sort of situation where like it's dense within the channel dimension, right? However, depth-wise separable convolution says, instead of doing this sort of mixing in the beginning, let's instead just do it like channel-wide. Like almost split our convolutions into like a bunch of basically color channel. But if you think about in the actual like deep inside the neural network, it's not color channels anymore. You have like 128 channels or 256 channels, right? So let's do it channel-wide, which is a lot more efficient because now it grows linearly instead of n squared. And then let's do the sort of dense thing, but this time instead of a kernel being 3x3, let's make it 1x1, which is the pointwise part of depth-wise pointwise convolution. So basically by doing so, we're still doing the spatial mixing and then, channel mixing operations, but we're kind of separating it out. And by doing so, we're actually reducing the number of parameters a lot. And another thing about quantization can get quite crazy. Like our team later with our LM section will talk a bit more about what people have been doing to do quantization. Like you can do like clustering of different network weights to like really make it like lower bits. But in most cases during inference, 16 bits, you cannot notice a difference in performance between the original 32-bit version and the 16-bit version, even in generative models, right? Like stable diffusion and stuff like that often come by default in 16-bit operations because it's so much faster to do inference on. And fun fact, the new NVIDIA GPUs, like have you guys heard of like the RTX 3090s and stuff like that, right? They have what's called tensor cores, and tensor cores specifically are optimized to do floating point 16 operations because it's much more efficient to do than floating point 32 operations. There are a lot of papers that bring this down to like int 8 or even int 4 from like Qualcomm and other places. That's kind of crazy. They do a lot of really weird methods with the weights where they do like further fine tuning on the weights themselves. But during training specifically, we usually want to stick with floating point 32 because sometimes when the gradient gets really large, you may get non-number NAN errors if you were to train on floating point 16. Because remember, this less bits you have for floating point, the smaller the range of numbers it can reasonably represent. That's some CS33 stuff. For the first years out there, you're gonna enjoy it next quarter. Anyway, so let's move on to the second topic, which is the landscape of generative vision. So then the question becomes, what is generative vision, right? So generative vision specifically is I want to compare it to what we have been talking about this entire time for all of our workshops so far, which is something called discriminative models. Discriminative models specifically is learning something. It's learning probability, specifically the probability of X, aka our input image, given the label Y. And you may be like, wait, that sounds really weird. What does that mean? Specifically, if you think about it, say we're doing a 10 class classification, right? Our output is a 10-dimensional vector. What each of the dimensions of the vector is really saying is it's saying, given that, given this input image, what is the probability that it will be of the label Y? Say that it will be of the label dog, or that it will be of the label cat, right? So we're learning P, Y given X. And specifically, we want Py given X of the correct Y to be really, really high, and Py given X of the correct of the incorrect Y to be really, really low. That's how we define our loss function. However, as y'all may remember when we talked about ResNets, discriminative model, at least with image classification, is kind of sort of considered a solved problem. In that we have kind of gotten better than human human perception at this point, and with something called vision transformers, which again our team will talk a little bit about later. We have basically found that we can just keep scaling up the models and just get better and better. There's not much point to do a lot of research in here anymore. So a lot of people have switched to something called generative modeling, which is learning P of X directly, aka it is learning the distribution of our input data directly. It may be like, P of X. What do you mean by that? Why P of X? And the reason why we want to learn P of X is because P of X tells us if you have a noisy image or some sort of really out of distribution image, like a noise image or image is all white, image is all black, or something like that, something that we wouldn't as humans consider as a natural image, if you will, then the P will be really, really low. So that P function, that intrinsic P function that we don't know how to represent, will say, oh, that's not really a number. That's not really a real image. However, if we give it a real image, it should be able to say, oh, the P is really high. I like that. That's what I want to learn. Right? So what we're doing is we're actually learning the distribution of the dataset domain. And what's really important is the dataset contains samples of the image distribution. It is not the image distribution itself. Because if we can just express the image distribution somehow mathematically, then there's no point of trying to generate images, right? We can just generate images with the formula we came up with. So basically, when we are given a data set of a bunch of images, that represents samples of what we want to finally generate, what we want our model to be able to generate. And specifically, we can also condition it with stuff. For example, what would the image X look like if we were to give it some label? This label can be, hey, I want to generate an image of a dog, right? Y can be dog. Or Y, in the case of what we call AI or stable diffusion nowadays, can be a text prompt with text-to-image models. So that's what generative vision is. And today, what I want to get to ultimately is something called diffusion models. So diffusion models, who here has heard of stable diffusion? Can I see it? Show of hands. Okay, we have everyone here has heard diffusion, stable diffusion, which is awesome, right? But the way that diffusion models work is basically, it is trying to map a noise distribution, which is really easy to generate, right? Gaussian distribution, we know how to generate that stuff, to an image distribution, which is really difficult to generate. And it does so iteratively. And specifically, the way it does it is you take in some sort of randomly generated noise that is the same dimension as our output image. It takes it in, and it keeps iteratively denoising that image. Basically, it takes that noise in, it denoises the image a little bit, and it feeds it back into itself. It denoises the image a little bit, feeds back into itself, and we keep doing that iteratively until we get an image output. And while this is happening, we can condition it with some sort of text encoder. And in this case, conditioning just means we're telling the model, hey, I want the image that's generated to fit this prompt. So that's a general overview. But this leaves a lot of questions, which is like, okay, how is it doing the denoising? How do you do conditioning? How does it know how much noise is in the image, et cetera, et cetera, et cetera? How does it know when to stop, right? These are a lot of questions that we're going to answer today. But to do that, we need to take a little step back. A little trip down memory lane, if you will, to see what is the current landscape of generative vision and how we even got here in the first place. So, yeah. And another way to think about diffusion models is if we think about kind of like all of our image space, right? Our entire image space. You know, in this case, this is kind of like a 2-pixel image. But you kind of think of this as a much higher dimensional situation where like every single dimension is a pixel in our input image. What we're really trying to do is say there is some cluster in that higher dimension which is really high in image density, aka most of the images are over there. And the other dimensions, which may be just pure noise, don't have a lot of images over there, don't have a lot of our data set over there. So as we iteratively add noise to the model, what the model is, by doing so, we're stepping out of our high data density. If we, say, provide a model with a real image and we iteratively add noise to it, we're stepping out of this high data density into somewhere with low data density. And we're telling the model, hey, this is what it looks like when I'm stepping outwards. And the model is trying to learn, when I'm outside, somewhere here, how do I map myself back into the image distribution? So that's the idea. That's why we do denoising and adding noise back and stuff like that. But before we even talk about that, we gotta talk about transposed convolutions. So we haven't really talked about transposed convolution so far because we have been doing classification. But and all we really care about is we have some sort of really high dimensional input image. We want to sort of squeeze that image down, extract a bunch of information so that we're kind of reducing its dimensionality. Transposed convolution does the opposite. It tries to increase the dimensionality of its inputs to the transposed convolution layer. Specifically, the way it works is, if you remember, how convolutions work is just you have a convolutional filter, you superimpose it with the image, you do a dot product, and you do dot product, dot product, dot product, dot product through an entire image, and you have a new filter, right? Transposed convolution does something a little different. Suppose we have this input, right, and we have these 4 kernels. What it does is it says, okay, well, these 4 are the same kernels, right? We just take this number, we multiply it with this kernel, and we just kind of put it on here, right? We take 2, we multiply it on this kernel, we just put it on here. We take 3, we put on this kernel, we just put on here, and so on and so forth, right? And then we take all these values, assuming the rest of the values are 0, and we just add them together. And suddenly, with a single kernel, we manage to up the dimensionality of our image or of our features. So that's very important because when we're generating images, we often start from a very, very small dimension. We want to sort of inflate it up and up and up and up so that we get to a really high dimensional image space. Is that going to make sense so far of why we want to use transposed convolutions? Okay, so basically, whenever we say convolutions in the future, this is kind of what's working behind the scenes. So let's talk about one of the first kind of attempts at doing image generation, which is something called variational autoencoders. So this was a paper from 2013, and specifically, its goal is this. This is its training goal. It says, we can't really sample this really high dimensional distribution, right? Because that's the image distribution. That's really, really difficult to sample, right? However, this smaller distribution in the middle, if we were to divide a network that an encoder that kind of squeezes down the image dimension, which is just like a classifier would, and reconstruct that original image to the same dimension, this tiny little dimension here, say just like a 128 dimensional space or something like that, it's a lot easier to sample. We can try to model that a lot better. So what if we do the following? We input an image, we let the encoder squeeze it down to some really low dimension, and we ask the decoder to inflate that back to the same image dimension, and we say, the way I want to optimize this, I want the input image and the output image, or the reconstructed image, to be the same. So the loss I minimize towards is the mean squared error. Yes?
What do you mean by sample the latent space?
Okay, yes. So latent space is this, right? The middle space, when we say latent space is usually a sort of lower dimensional representation of our data. Usually it captures the most important information of the data sets. That's kind of what it is. So like the middle space here we'll call the latent space, and the outer space here we'll call the image space. Does that kind of make sense?
Yeah.
And for sampling specifically, it's saying the following. if you have a Gaussian distribution, right, you define it with some mean and some standard deviation, you know how to sample a thing from that distribution. You know how to say, I want to generate a vector depending on a Gaussian distribution. We can do that really easily, right? Because we have a mathematical expression of how to do that. However, if I want to say, okay, here is, imagine a distribution of all possible human images, of all possible images of a cat, or all possible images of a dog. Sample an image for that. You'd be like, huh? What do you mean by sample image for that? We can't really do that, because this is a distribution we cannot mathematically define. So, basically, our goal is saying, if we have an image distribution that we cannot sample, because it's, the image distribution is just amorphous thing that we can't really define. All we have is, samples of the data sets. And you can say, oh, randomly pick an image from the data set, but there's no point in doing that, right? So our goal is to try to compress that image down into a distribution that we can more easily sample. For example, what if I enforce this to be a Gaussian distribution? Then I just say randomly generate a Gaussian vector and just reconstruct it with a decoder. Does that kind of make sense?
Yeah, so then you can just sample something random from the latent space and then put it through a decoder to get something in directional distribution.
Bingo. That is exactly what the goal is. That's what a VAE is, kind of. The VAE was originally created just trying to compress an image. It's almost like for image compression. It's like, oh, we have this really high dimensional image, but all images, there's a pattern somewhere. So can we just extract 128 dimensions of the most important information that we try to reconstruct it, right? But what VAEs did, specifically variational autoencoders, that's what this is an autoencoder. Variational autoencoder said, okay, whenever we're given this image, I want to instead predict two things. I want to predict the mean and standard deviation of what I should multiply my sampled Gaussian vector to be to reconstruct that image. And specifically, that changes a lot because what we had before, this distribution is still really weird. It's much lower dimensional, but it's still really, really weird. Because we are never enforcing the distribution to be, say, a nice, smooth Gaussian distribution. It can be really weird and jagged, right? However, if we were to say, oh, you're predicting a mean and standard deviation, and I'm sampling this from a Gaussian distribution, that basically forces the middle distribution to follow a Gaussian distribution and for us to actually be able to sample the middle. As I was saying, we sample it in space and we generate an image. Does that kind of make sense?
Yeah.
Yes.
Doesn't that catastrophic, massively reduce the amount of information you can fit in any given n vector? Like, you have a vector 10, you could fit so much information in there, but now you can fit like nothing. I feel like it's because
the Gaussian distribution.
You're effectively all you're doing is you're compressing it to two numbers, right?
Specifically, this mean and standard deviation is kind of dimension-wise.
Oh, okay.
Yeah. So this is not as flexible as our image generation models today, where it's
it's not one. Okay, I thought it was.
Yeah.
One.
So to be able to generate an image, what you will need is kind of like a reference image to be like, oh, this is what I want my rough standard deviation and mean to be, and then you're able to kind of generate variations of that face that kind of share this or same original input faces feature. It's not generating completely from scratch.
Actual list of means.
Okay,
Yeah.
and it's the same length as your vector.
Yeah.
Yes, it's the same as your vector. So it's kind of like a point-wise multiplication, that sort of stuff. Yeah. Again, the VAE is actually kind of complicated in terms of the math. They do some elbows and stuff like that, some marginal errors. We're going to get into that state, but that's the kind of idea to begin with. Is can we compress this image dimension to some smaller dimension that we can much more easily work with? That's the first idea of doing image generation, and the results looked pretty good. These were the very first results. What you can see here is that they trained this on the MNIST data set. You guys remember what MNIST is? The Hadron digit data set, right? They're like, hey, if you were to encode the number 7 and encode say number 1, then number 6, and number 2, we can actually kind of interpolate between them, in the middle Gaussians, and we actually get this nice and smooth interpolation. This is a very interesting finding because what it tells us is that when we're trying to compress images and stuff like that, the latent space is smooth. That's a very important observation because then if the latent space is smooth, we can do a lot of fun things with it, like interpolate two images together and stuff like that. And it shows that the latent space is almost like well compacted. It is rich with information. So when we're doing interpolation, we're always staying within, after we have decoded out the outputs, we're always staying within the image distribution of something sensitive, which is really nice. And you do the same faces. Like, you see there's a smile here, this guy is really, really angry, and you kind of interpolate between them. And then there's a later work called VQVK. It's called Vector Quantized Variational Autoencoders, where instead of just learning a mean and standard deviation, instead, while it's training, learns a sort of vector of embeddings, right? It learns a sort of vector of embeddings of means and standard deviations, and as it has a library of mean and standard deviations, it goes, okay, cool. I have that vector of mean and standard deviations. When I want to generate an image, I can randomly pick something within this library, and I can, randomly generate a Gaussian, use that randomly picked mean and standard deviation to multiply the Gaussian, and then generate the final image. And now what allows you to do is not have to have some sort of reference image to begin with. And you can kind of generate, in this case, a arbitrary faces. But the issue with that is, because we're still limited to this library of images, the final distribution is still kind of limited. Like, for example, we can only generate, say, pictures of people. Or we can only generate, say, the entire image in that data set, which is a pretty big data set, but we can go more, right? So by its inherent design, it is very difficult to scale up VAEs. Yes?
So when you say that the latent space is smooth, does that mean like within the latent space you can't like approximate like, oh, here's a subspace where, for example, M is like within the latent space you have a subspace that is roughly all the like 1 digits, and one that's roughly all the 2 digits?
Yeah. When I say the latent space smooth, specifically what I'm referring to is, as you are in this like Gaussian latent space, right? The smaller latent space in the middle, it's much lower dimensional, right? As you kind of randomly roam around this latent space, whatever gets generated as you roam around this latent space, you kind of generate the intermediate outputs. That's going to look like a sensible image, if that makes sense. That's going to look sensible. Like it's going to look like a normal image, like in this case of evidence, it's going to look like some sort of handwritten digits, right? So what that really means is saying the latent space is rich, aka there is no part in this latent space that we're wasting, if that makes any sense. Anywhere in this latent space, we will generate an image that makes sense, or we'll generate an image that's within our data set distribution. Does that kind of make sense?
Yeah. So another question is, does that mean that you can like roughly divide the latent space up into somewhere where almost every part of it means like a digit, for example?
You are exactly correct. You can, in fact, something that you can actually do is kind of say, okay, after I've trained this model, let's say I did MNIST, for example, right? For each of the 10 classes, I want to pass in all the images and look at what its latent vector would be. Then then what you can actually do is try to visualize what you call it each cluster in the latent space each number occupies by doing something called principal component analysis, PCA. And you can find basically it finds like the top most important dimensions in which this latent space, these latent space vectors are at, and you can actually kind of visualize. We don't have a graphic here, but you kind of visualize ones are over here and twos are over here and threes are over here. It's really cool, and it kind of shows that when you go from 1 to a 2, it's kind of stacking between here. Somewhere in the middle, it may look a little bit weird, right? It may look like that's like a weird number between 1 and 2, like a slightly squiggly 1, for example. But as you get to 2, you're like, oh, that's a 2, definitely. So you can do really cool visualizations like that with VAEs. So principal component analysis, PCA. This is something that you will also probably touch on in your Math 33A class as well. It's a very decently common-ish linear algebra technique that's still being used today, because whenever you have really high dimensional data, aim to figure out what's kind of like 2 primary dimensions that you can use to visualize my points, it's a really useful technique. Yes. Yes. Yeah, actually there is. I'm trying to bring up the slide right now. Theory track number 3, number 4. Okay. Sparse doesn't have to open, but yeah, you can do the same thing with embeddings, and that's how if you guys remember from our LLMs and embeddings workshop, we talked about how you can do man plus woman minus man plus or king minus man plus woman gets you a vector similar to queen, and the way we kind of visualize all of that, you can do that with PCA. Yeah. Okay. Then there comes something called generative adversarial networks, which is from this pretty legendary researcher called Goodfellow, right? Goodfellow, if you take Jonathan Cowell's ECC147, which is a class I absolutely rave, that's the textbook that he will be using, but written by him. But in 2015, he proposed this thing called generative adversarial nets, and it works drastically differently from how we have been generating images so far. Specifically, we have 2 networks, a generator and a discriminator. What a generator does is it takes some sort of noise, it takes some sort of really low dimensional noise, like a 128 Gaussian noise sample, right? So we just keep randomly sampling things. And it uses a bunch of transpost convolutions to generate some sort of image. At first, that image will be really, really noisy, right? Because you imagine networks randomly initialized, that's also a random noise, which is going to get crap over here. However, the really interesting thing is, then we train a discriminator. The discriminator is just like any normal binary classifier, where it takes in that fake image, goes in, and it tries to tell, is that fake image real or fake? Because at the same time, we also randomly feed it real images from our actual data set and we ask, is that image real or fake? So basically the generator is trying to fool the discriminator, while the discriminator is trying to tell, is this image generated by a generator, or is this image generated by or is this image from the actual data sets? And you can imagine that the generator is really bad in the beginning, and the discriminator is really bad in the beginning. But as we train them at the same time, they both get better. So if you think about it, when we reach some sort of local minimum, aka the discriminator is able to tell between a real image and a fake image really well, but at the same time, the generator is also able to fool the discriminator very often. Then we have basically, if the generator is able to fool the discriminator, it must be generating images that looks like it's from an image distribution. Does that kind of make sense?
Yeah, can the discriminator get like too strong though if you have both of the models working at the same time?
And that is actually one of the challenges again. You have exactly mentioned that. You have to be very careful with the learning rates and the tuning and the network sizes of the generator and the discriminator. Because if the discriminator gets too good, the generator will never learn anything, right? If the generator is too good, and there's actually a problem in GANs called mode collapse, which is the generator finds one really weird type of image, like let's say a human face with eyes, with like 6 eyes over here, that the discriminator, for some damn reason, is really, really bad at discriminating that, saying, oh, that's a fake image, but the discriminator keeps thinking it's a real image. Then the generator will just say, oh, okay, the discriminator is awful at that. I'm just going to keep generating those images. And the discriminator could never figure out that that's actually a fake image. And you actually have a really, really bad generator at the end. So GANs, at least on the smaller scales, is actually kind of unstable to train. And there's like a lot of papers that try to make it more stable. However, if you are able to get GANs to train, and you will actually, this is actually one of the projects that you'll be doing if you were to join Project Track, though. We use GANs to generate emojis. We can see, even from the first paper, the results are actually pretty good, right? The sharp lines and get like, these faces. And, later we have this paper called Style GAN, which I'll quickly go over. But before that, who here has seen this person does not exist.com? Okay, we have Julie. Sorry, what's your name? Rathul. Right, Rathul here has also seen it. But basically, what this website is, if I click on it for a little bit, Control click, is basically, as you refresh this website, it gives you a picture of someone new that's generated completely, like this person does not exist, by a generative adversarial network. And that's what's behind it. And specifically, it is a variant of the generative adversarial network called the Style GAN. I won't get into too much detail in this because motivating a lot of this is really difficult, but specifically, what Style GAN is, it's an architecture paper. It proposes a new architecture for generative adversarial networks that's basically still the state-of-the-art thing. Specifically, instead of just like what we had before, generating from a starting noise all the way to some sort of final image, all at once, it separates the task into twofold. First is the map step, where it takes in our kind of starting Z or our starting noise latent, our starting randomly generated noise, and just passes through a crap ton of fully connected layers with like gray moves in between. And that gets us Zoom quit unexpectedly.
Oh.
Incredible. Okay, hold on, let me share the screen again. Okay, anyway, we're back. So, what this does is it says, okay, and we end up with a vector that's the same dimension as this original Z. So we kind of transform the Z so that this maybe contains a little bit better information. Then we have the synthesis network on the side, where we start with some constant 4x4x512, constant tensor. And that tensor is also almost like part of your weights that you're learning. And it keeps inflating that tensor, and at the same time, injecting this starting, what we call style vector here, into every layer of the tensor with something called add-in, which is basically just saying we have this, we have a layer. I want to use this vector to linearly project it into a mean and standard deviation of this add-in and just kind of like multiply it with that. So it's the normalization plus sort of scaling thing. And we're also injecting noise in the middle. And this process, by separating this sort of original sort of like style vector generation process and the synthesis process, actually is able to generate images that are extremely high quality. That looks something like this. Any questions so far?
Is this also more efficient?
It is also more efficient because instead of starting with a much higher dimensional vector, you're actually starting with this like lower dimensional vector here. Like if you want to scale them up to the same amounts, this will perform much better. There really isn't an efficiency thing per se because these original GAN networks, people have tried scaling it up a lot, but they realize it doesn't scale that well, so people never make too big versions of them. But style GANs scale really, really well, so people usually make much bigger versions of them. So because these are usually much bigger, we don't really. It's hard to compare which one's more efficient, if that makes sense. Yes. The style you inject is from this, which is at the output of our mapping network. No, the style is starting. It comes from this W vector, which is what we call our style vector, which is the output of if we were to pass our initial random noise through this mapping network. And specifically, we're doing this projection process where like there are weights that projects this proper dimension that is able to scale our features, our intermediate features of all the layers. Yeah, these are weights. Yes, these are weights. But then, yeah, you're using these weights to do like a linear projection, actually, like Wx plus v, all of this W over here for every single layer because of the difference in dimensionality, right? And specifically, what's really awesome is StyleGAN also has something called disentangled latent space. What exactly does that mean? You may be asking. Well, it is this. Before, when we had a normal generative adversarial, if you were to do interpolation in the Z space, it usually worked pretty well. However, the issue is this. Say I have a person, I have a picture of me. That's just, me. And then I have another picture of me, almost identical picture, but I have glasses on. And I were to say, and I were to somehow magically find the original latent that would have generated these two pictures. And we're going to try to interpolate between them. The issue of what's going to happen is as we interpolate, you would think what will happen is the image doesn't change, but my glasses just slowly fade in as I interpolate between me with glasses and me without glasses. However, maybe in the middle, as I'm interpolating, I'll suddenly smile for a little bit, or suddenly my face will turn for a little bit, or suddenly my facial features will change and then change back. It is a smooth latent space in that every single point in the middle as we're walking through is smooth, but when we do this sort of interpolation, the features are not disentangled. So it is very difficult for us to separate features like, for example, is this person smiling? What color is their hair? Do they have glasses on? Do they not have glasses on? Etc. Etc. And what StyleGAN realizes is that after we have done this sort of, mapping, if we do interpolation within this space over here, we actually have really disentangled features. We're able to, do interpolation between a picture of someone without glasses and almost the exact same picture but with glasses, and have the glasses just slowly appear, and it's really nice. And what they realize is that the different layers of style injection also allows you to make styles from other images and stuff like that, and you're able to almost composite images together and create really cool effects. Yes, RT.
What forces the mapping network to actually learn to disentangle the features?
Right. What forces it to do is because the thing that makes these images actually generate images that are unique from each generation from different noise is it is getting directly affected by our initial W, right? Our initial W is almost directly being fed into these adaptive normalization layers and actually directly affecting our outputs, right? Unlike with our traditional thing, where you have a latent that affects what's here. But as you get deeper and deeper and deeper and deeper into a bunch of convolutions, the effect of interpolating this gets kind of muddled up by all these layers in between, right? So there's less of a direct mapping between our initial latent, or the thing that we're injecting, the thing we're interpolating in, versus the generation process. So by having this sort of style injection be literally one linear projection away, it has a much more direct control over what the final output image should be, and thus it is able to have this disentanglement a little bit more. There's probably better explanations out there of why it's disentangled, because the motivation of why we did the StyleGAN thing actually came from a prior stylization paper that people did. They were like, oh, we can use ADA to do stylization, and this author basically went, Kados et al. Basically went, Kados et al. By the way, an absolute titan in generative vision, basically went, hey, what if we apply this to the generative adversarial network to generate images? I believe that this entanglement is something they noticed as they were playing around with it. So I don't know if there's a great sort of explanation of why when we do this training we're able to get a sort of W space, as we say, that's very disentangled. Okay, so summary so far. Yes. Disentangle as in features. So instead of when we are interpolating in our spaces, instead of just oh, my face slowly transitioning into another face, there's this sense of a direction within the space represents some sort of feature. Say, do I have glasses on, or how round is my face, or what orientation is my face turning, or what color is my hair? how big is my nose, stuff like that. What direction is the light? Like it's things that are more like human describable, if you will, human interpretable. So the summary so far is, the pattern is that most of these things seem very, very unstable and jank. Like as you were mentioning, like GANs, that seems like it's very unstable, right? Being in regressive models, I talk about regressive models in a private class I never caught on, but GANs, however, are still very amazing. Like there's papers out there that still use GANs to this day. But these models were very dataset dependent, right? You can usually only generate one class of images, like like human faces or cats or dogs. So like the most people have scaled these up is ImageNet, which is just 1,000 different classes. But it's a very limited type of image type. So the question becomes, how do we go big? And this is when we get to diffusion models, which is the basis for stable diffusion and all these AIR things you have been seeing today. Specifically, if we were to kind of recall what we were talking about in terms of diffusion models, we're showing a model what it looks like to get out of high data density images to low data density images, aka good looking images to very noisy looking images. And we're asking the model, now you have seen how that works, can you do it backwards, right? Starting from noise, can you slowly move yourself back to an in distribution image? So with that in mind, we have something called diffusion models. Specifically, the DPM, the denoising diffusion probabilistic model, is one of the first works that kind of proposes and showcases this as a really viable way to have. It's like a new paradigm of generative modeling, because at this point, GANs were the king, and people are like, oh wait, this is new. Specifically, it is a denoiser that is so good that it generates an image from pure noise. And the way it works is this. You start from some sort of X0 image. You iteratively add noise at some sort of predetermined time steps. So let's say we have 1,000 time steps, and in each of those 1,000 time steps, I associate a sort of noise level with each one of them. I kind of add noise iteratively until I get to the time step. Then, and this is what we call the forward process. And then what we try to do is we say, okay, so now we have seen what it looks like to add noise. Let's try to make our neural network learn the reverse process, aka given the noise of x of t, what is the noise? How do we get back to x of t minus 1? So that's the general idea. And specifically, the model is trained as follows. So I feel like if I explain the training loop, the way that this model works will be a lot clearer. So we have this model, that's AUS, and we start by choosing a random image from the dataset, right? And then we say, okay, then let's choose a random noise level t from our kind of uniform list of t's. And then we sample some random Gaussian ones from the normal distribution. Again, we can do that very easy. And this is how we train the model. First, we want to add noise to the image based on some sort of noise schedule alpha t. You don't have to worry about what alpha t is specifically, but specifically, look at this. What we're doing is we're saying we're taking the image, multiplying it with a certain constant, and adding it with the noise multiplied by a certain constant, right? And the reason why I have this alpha t and y minus alpha t situations because that ensures our variance stays about the same, or variance stays controlled. But we're mixing the noise and the image together according to our time step. The higher the time step, the bigger this coefficient will be. The lower the time step, the smaller this coefficient will be, and the bigger this coefficient will be. So in other words, the lower our time step, the less noisy the result will be. And then step 2. This is our model, epsilon theta, which is very confusing because they use epsilon for both. But epsilon theta specifically says, okay, given our noisy image and the current time step t, predict the noise that I just added. That's very important. We're predicting the noise that I just added, not what the image will be at time step t minus 1. Is that going to make sense so far? So we just added this noise to the image, and we made the image really noisy. And we're asking the model to ask the question, what noise did I just add? And it's trying to predict what that noise is. And specifically, then it takes that output and then tries to minimize, in this case, like norm square, which is mean squared error. It tries to minimize the error between the noise that our model predicted that was added, but the actual noise that was added. So basically what the model does is when you give it a noisy image, it is going to be very confidently say, oh, that's the noise you've added. So if you say subtract the noise from the original image, we can get some sort of really clean output, right? Does that kind of make sense? The reason why we do so is actually because of training stability. A lot of what people have realized that when people have applied diffusion models to like other types of data sets, like driving trajectories or stuff like that, they realize, oh, it's actually fine to just predict not the noise, but the image itself. But the issue with that is in order to try to predict the image itself is varies very wildly in what its distribution looks like. But noise, Gaussian noise, always looks about the same, right? So because of that, it is a better, smoother distribution for the model to predict, and that usually leads to more stability. And we will also have a bit more of a mathematical sort of motivation for that in a little bit. It will kind of make sense a little bit more. But we predict the noise instead of the final image because the authors originally found, hey, that's more stable. Does that kind of make sense? Yes.
So alpha t is a function of t.
Yes, it is basically a list of coefficients, right? Like alpha 0, alpha 1, alpha 2, alpha 3, all the way. It's just a list of coefficients, that we define. Yes.
That equal the distribution of the image or like generative image then? Like with a minus sign on that?
Kind of. It is trying to map the noise distribution to the image distribution, right? If you start from noise distribution, you're trying to go back to the image distribution. Now, again, it'll become a little bit clearer when we actually see what this really means intuitively. Okay, so then how do we actually generate an image? This is how we do it. First, we start with some sort of Gaussian noise, and we call it x of t, because x of t means that's the most possible amount of noise I can add to this image, aka it is just pure noise. We know how to sample that. Then, at time step t, with an image x of t, first, we predict the noise in xt. So this is actually the model saying, hey, okay, given this really noisy image, this is the noise that I've added. Then, you say, then we want to subtract that predicted noise from xt to get a predicted denoise image, right? And you would be like, oh, why don't we just use this? Like it's like one pass. Like we predicted the noise image. However, the issue with doing that is, if you think about it, when the model gets a really noisy image, its final x0 prediction, aka when we subtract its predicted noise from our inputs, will be really, really bad. Will be really, really blurry, right? However, if we give it a less noisy image, its final output after we subtract the noise I predicted will be much clearer. Will be much more like an actual image. So what we want to do is somehow be able to kind of scale our noise out, give the model more chances to be able to predict what the final image is. And specifically, the way to do so is we want to add slightly less predicted noise back so we get to the predicted x of t minus 1. To reiterate again, when we're at x of t, I want to say first, what is model predict the noise that I've added to this image. Then you say, okay, model, given that noise, I can then just mathematically calculate what the model thinks that x0 will look like. And then I add back the noise the model predicted, but slightly less this time, to the point when we have the equivalent amount of noise as we were at x of t minus 1. Does that kind of make sense?
So we're not predicting xt minus 1, we're predicting x naught. So that it gets x naught.
We're not really predicting x naught. We're predicting how to get to x naught. The delta image or the delta of noise, the added noise that would get us to x naught. Does that make sense? Yeah. So it seems very convoluted, but again, I promise it will make a little bit more sense in a little bit. And the really awesome thing about this is instead of going from x of t to x of t minus 1, we can actually also just skip time steps. We can say, what if I go from time step 1000 to 900, and then to 800, and to 700? Because we can control how much noise we add back, which controls what time step we have gone back to, right? So, by doing so, instead of having to do inference 1,000 times, because we have 1,000 time steps, we can skip some time steps, and empirically we find that's good enough. The generation quality is like a little bit worse, but it's not that much worse. So, in fact, with stable diffusion, you may have heard like 50-step generation or 20-step generation. That's what that's referring to. We're actually just skipping time steps.
Do you know what the reference step size is? Like the first
Yeah. So, yes, that's the sort of reference step size. That's kind of like been the very first VDPM paper. That's what they trained it with 1,000 step sizes because they realized, oh, if you do any less, the model doesn't perform as well. So that's kind of just became the norm. But like I think with like much bigger scale models, they may train it with more time steps. But that's what we usually train it with. Yes, of course.
Why is there a random noise term?
Right. What the fuck is this? Why do you have this random noise term, right? Do I explain? No, I don't. Okay, so basically what the random noise term is originally, the reason why it's there is originally the DDPM paper actually modeled this whole thing as a Markov chain because they're like, oh, we have this x of 0 process all the way to the end, but we want to make it a Markov chain because instead of doing this iterative noise adding process, because in the model is not predicting what went from x of t minus to x of t. It predicts directly to what's x naught. So they're like, oh, that's bad. We gotta make that happen somehow. And the way they realized after doing a bunch of probability math, like the paper is absolutely horrendous if you look at the math. But what they realized is that, oh, we can actually just add back random noise, and it will kind of be mathematically equivalent to our Markov chain. And basically what this DDIM paper, the noise diffusion implicit models, which happened around 3 months after the original DDPM paper, is basically said, hey, we don't need to do that. Like, we don't really need to do that. We just do this and just like make this random noise a sort of parameter we can control. And specifically what people found is if you just, by injecting a little bit of noise in the middle, you actually improve the generation quality by decent amounts. It's like noticeable when you benchmark it, but like, you know, like slightly visible, but it's not that much of an improvement. So, but the bad thing about adding noise is that you can imagine how then the generation process becomes less deterministic, right? Because we're adding noise every single time. We can't promise, oh, every time I generate starting from this noise vector, I'm going to generate the same image. One of the things that you actually find is that if you don't add noise, if you just like set the noise constant to 0, you can actually still do the same interpolation. You can interpolate in the noise space, and you can also, like, the same interpolation will happen in the image space, which is pretty cool. But yeah. So, y'all asking, why are we predicting X? Why are we predicting all these things? And the reason is because what then, Karas et al., which is, hey, the same author as the Stockton paper, and also Yang Song, which is also another titan in diffusion models. Basically, Yang Song first came along and says, hey, diffusion models are just SDE solvers. So you're like, what the hell is an SDE? It's something called a stochastic differential equation. And the way we look at this is, remember what's actually happening. We have our prior distribution, which is a fancy word to say our noise Gaussian distribution, right? And we have our image distribution. As we are adding noise to the image, what's really happening is that is tracing out a differential equation path from our data distribution, from an image distribution, to our noise distribution, right? So when we're saying the model predicts delta x, what it's really saying is, say we are at x of t, which is somewhere here, right? What is the direction I should go to get back to the data distribution? So it's the delta t, the delta in our differential equation. Who here has taken math 33 before? Like have taken differential equations. So you kind of remember that, right? Like Euler solvers, where you find out what d of x is and kind of use that to trace out what the function looks like. It's the same thing here. Our delta, in this case, is the noise, because it's telling us how we can get from x of t to x of t minus 1, right? We're going through this delta of this differential equation. And what Yang Song said is, hey, that's actually the exact same formulation as the stochastic differential equation. And that's nice because the stochastic differential equation is perfectly solved by this one paper from 1982. And they used it and they were like, cool, that's a paper. Anyway, and that's actually a pretty important paper. But Karas et al. Said, okay, we have all these, this probability framework with Markov chains, we have this like SDE framework with all that. All of this is actually just saying diffusion models are really what they call a probability flow ordinary differential equation, which is a fancy word of saying we're mapping from the noise distribution to the image distribution, and the path traces out a differential equation path. And what the model predicts is the model is our delta. The model predicts that delta, which then we can use differential equation solvers to try to map from the image to from a noise distribution back to the image distribution. Specifically, some later papers do actually do this, where they're like, oh, this process over here, this is actually mathematically equivalent to the Euler solver, and we can use other like fancy second order solvers to make this process better. But that's besides the point. The point is, it's actually just an ordinary differential equation, and that's image generation. Yes.
So is that an inference type optimization?
Yes, it is an inference type optimization, because if you think about it, the more time steps we're skipping, the bigger steps we're taking while we're doing this, right? So at the cost of quality, we are gaining inference time because we're passing the model back to the image back to itself, or the image back to the model less times, right? So again, to summarize, we show the model how to map from data to noise, and the model learns to map from noise to data. So yeah, UNets is really just a way to just the architecture. Let me see what time it is. Ooh, 13. Okay, I'm gonna speed up. So UNets is the network architecture that's actually behind most diffusion models, and specifically the way it works is basically you do like a bunch of convolutions. You downsample, convolution, downsample, convolution, downsample. It's basically an autoencoder, but then you have these long skip layers that allows us to kind of pass layers in between, and that makes the output and the input the same dimension, and you also add in like self-attention layers, which basically allows the model to kind of enforce a sort of self-structural coherence, and also you inject the sinusoidal T, which you may remember from the large language model stuff, it's it's all but the point is that's what the network is. That's what the actual network that we're training with is. This is usually what's the backbone of diffusion models. But diffusion is really referring to a training scheme than an architecture scheme. That's just what people tend to use. You will actually next quarter, the very first reading group I'm doing, low preview called Everything is Diffusion. I'm actually going to talk about the new advancements in architecture for diffusion models. Where actually, for example, have you guys seen Sora by OpenAI, like their new video generation models? That's like absolutely insane. It doesn't actually use the UNets because UNets don't scale that well. They actually use something called a vision transform, and I'll talk about that in that reading group as well. But yeah, so then it becomes, okay, how exactly do we actually do text encoding? How do we actually inject this text encoded information, right? And the answer, at least what we have so far, is something called clips. So one of the ways you can actually do this is by just saying, okay, we use a large language model. These large language models are able to encode text into embeddings pretty well, so let's just use those. That works. But OpenAI's solution, when they first came out with DALL-E 2, if you guys remember that kind of made waves, is something called clip. So what clip is it says we have a data set of a bunch of image and caption pairs, right? And we pass batches of those image caption pairs, the captions into a text encoder, and the images into an image encoder that has the same output dimension. Specifically, then it says, here's our training loss. The image and caption pairs that actually match, aka are diagonal, I want that value, the dot product value, to be as big as possible. And then, for the image and caption pairs that do not match, aka they're not matching images and captions, I want the dot product to be as small as possible. If you may remember from vector calculus or just vector mathematics, the dot product represents how close the direction of two vectors are. If the dot product is really big, that means the two vectors are pointing in a very similar direction. However, if two vectors are, say, perpendicular to each other, then the dot product is 0, right? If two vectors are pointing completely opposite from each other, then the dot product is negative, right? So by trying to maximize the dot product between the embeddings of text caption pairs that match, and trying to minimize the dot product of the embeddings between text image captions that are not actual pairs, what we have done is basically force the model to be able to encode images in the same embedding space that it does encoding text. Which means, say when we give it a text caption, what we're able to do is be able to claim that, hey, this text caption is going to contain image information. And the reason why it's going to contain image information is because it was trained joining with some sort of image encoder. So it must be in a space that contains image information. Hence, we can use that for generative vision. Does that make sense?
How do you train the text?
Oh, we train them at the same time, right? And the way we train is just, the dot product loss that I was talking about, right? You just backpropagate to both of them. You just train them parameters. You train them at the same time. Does that make sense?
Yeah.
Yes.
So P1, P2, etc., and I1, I2, etc., they're both vectors?
Yes. They're all just vectors. They're embeddings, basically. Okay, so that's how you do I clicked on the paper accidentally. Anyway, that's text conditioning. And the last thing before we get to diffusion models, stable diffusion models, is something called latent diffusion models. To motivate this, currently, before that, all the diffusion models we have seen are like 64 by 64 in resolution. The issue is UNets are very expensive because you're going from big to small back to big, right? Unlike GANs, we're just going from small to big. So you have this whole other half of model that you have to worry about. And what we have realized is diffusion models usually require a lot of different layers, and each layer has to have a lot of different channels. And that's very inefficient. Say we want to generate 512 by 512 images. That's extremely inefficient. How do we fix this? How are we able to generate images in a much smaller space? Enter back our VAEs, our variational autoencoders. Specifically, latent diffusion does the diffusion process in the latent space of a VAE. You're like, huh? What the hell does that mean? This is what it means. So let's say we have a data set of a bunch of 512 by 512 images, right? We first train a first stage model. We call it first stage model because we train it first, and it's like a complete separate stage for the rest of the diffusion training. We train a variational autoencoder where all it does is it says, I want to take a 512 by 512 image, compress it down into a 64 by 64, some sort of latent space, and I want to reconstruct that back to the 512 by 512 image. I want to make an almost perfect reconstruction, right? So that's what it says. The first thing is you train a variational autoencoder that's able to do that very well. Then what you do is for every single one of your training images, instead let the diffusion models do diffusion within the latent space. Specifically, you're doing diffusion within this much compressed latent space. So when you're actually generating an image, because you start from a 64 by 64 pure noise, you generate some sort of latented image, and you just pass that through a decoder, and you get the final image. And by doing so, we have essentially trained a 64 by 64 diffusion model that is able to, after passing through our VAE decoder, be a 512 by 512 image. Does that kind of make sense? Yeah, that's pretty cool, right? And that's the architecture behind Stable Diffusion, and how Stable Diffusion works is we have this text encoder from our clip, right? It comes up with a vector. We inject it with cross attention, which you may remember for LMs, like into the image. And at the same time, we have this noise that we're kind of doing this iterative denoise that we talked about. We have an image within the latent space, and we pass it through a decoder to get our final generated output. Yes. In most architectures so far, cross attention. So basically, if you remember, like each layer has self-attention. Usually for these models, right after you will have a cross attention that kind of is able to take in that text and kind of like manipulate the image based on that text encoding. Again, I go into way more detail about this in my reading group. Yes, Julie. What do you mean out of band decoding problem? Yeah.
Outside limits you, like there's not an image.
Yeah. The hope is when we remember VAE spaces are smooth. So when we give it enough images, instead of just encoding the space of what our input images is, it is able to encode all possible images that humans find sensible. Or like humans find, hey, that's an image, that's possible, and that's drawn by someone or taken by someone, right? So it is able to capture stuff like this. Yes. There is. Again, I talk about this a little bit in my reading group, but basically, Adobe around 2022, like a few months after Stable Diffusion, came out with GigaGAN, which is basically they said let's scale up StyleGAN to so big that is the same. Like this thing's 1.4 billion parameters. They also scaled it up to 1.4 billion parameters and said, hey, we get the same generation quality output. But the issue is Stable Diffusion was open sourced, so researchers can do a bunch of things with it. GigaGAN wasn't open sourced. So we couldn't really play around with it. There really wasn't a way for us to actually check how good it is because the community, the online community, didn't really get they can't get their hands dirty around with it. So that's why Stable Diffusion is so important. It's not just because the latent diffusion model is really important. Stable Diffusion so the latent diffusion model came from like a German lab, and Stability AI, which is the company behind Stable Diffusion, went to the lab and said, hey, that's really interesting. We're going to give you a shit ton of computational resources. Let's train this together. And then they made it open source. Because making it open source means that so much, like ML scientists can do so much with this model and play around with it and find all sorts of things, like controllable generation and stuff like that. Yes. They have a business model. You can see with like their newer things, they have tried to be like, oh, we have a business license and stuff like that. They are trying to make some money now. They're still kind of in that sort of startup mentality of like we get a bunch of venture capitalists to throw money at us, and eventually our models will get so popular and so good that we can start charging money for businesses and we'll make money from that. I'm not terribly clear how they actually make money, but again, I'm thankful that this exists. Which is like my research is in controllable generation, and if Stable Diffusion never open source their models, my entire field will not exist, and I think that's kind of crazy. So yeah. Anyway, so what you have seen is actually just a portion of my diffusion reading group. A little bit ago, like I built up what these things are and I talked about like what ML scientists have been doing with these models, and you can actually find it on YouTube. Like this was last quarter actually, the week now last quarter, and you can kind of see a little preview of it. We talked about controllable generation, we talked about video generation and 3D generation, and we also talked about a lot of really other weird papers that have used diffusion to do other stuff. So yeah, again, you can find like the reading group over there where I talked about that. Anyway, any questions before we move on to reinforcement learning? Okay, cool. Let's talk about reinforcement learning then. Yeah. One thing we may run a little bit over time today, because I may have spent too long talking about diffusion models.
I'll run through it a little quickly.
Yes.
So we'll talk about reinforcement learning, a really fascinating area in machine learning. Let's get into it. So let's enter into the real world, right? So a lot of real world problems have this sort of sequential decision making. They're sequential decision making problems, right? Say, for example, you have a robot and you want your robot to pick up cans in school, let's say, or you guys know the little robots that go around at UCLA and give you guys let's say you order
Cocoa.
what?
Cocoa and stuff like that, right?
Yeah. And like you got
Oh, yeah.
those little cool robots that bring you food and so on. Say you're those robots, right? You want to train machine learning models to perform those tasks, right? Such as picking up cans, or giving us food when we need, and so on, right? Say you have those type of problems. Currently, using the sort of current framework that we have, it's very hard to train those models, and very hard for those models to perform tests on you, right? And so there's a sort of complexity to them. And the reason for this complexity is because a lot of these tasks aren't differentiable, right? Like, how do you differentiate picking up tasks? Like, how do you tell a model, oh, you're doing a good job at picking up a can, or you're doing a bad job at picking up a can, right? That's pretty difficult to do, right? Because it's not differentiable, right? But it's pretty easy to say, oh, this is an apple, and this is a cat, right? Because if it's wrong, we can just say, what's the optimal answer? Just take the difference between that and backpropagate the model.
And the important thing is, with like classification, or like old class we have been dealing with, the loss function itself, like mean square error, like we know how to calculate gradient for that. But what if you're dealing with not just a simulation, but like a real world, a robot arm trying to pick up an apple, and you're like, oh, you've done a good job. How is it able to backpropagate through the real world, through physics? Like, you can't do that. So suddenly we can't just dab gradients anymore. What do we actually do? That's where reinforcement learning tries to solve as well.
And that's the view of it. That's what makes it so interesting. So just to give you guys a glimpse of how RL is different from just our standard RL approaches. So one big difference is that supervised learning, the learning that we've seen on some uses explicit and labeled training data, right? While reinforcement learning doesn't use it. In fact, the data, it actually collects it while it's learning, right? So we don't have this sort of training phase, it's training as it's going. So the robot may be training as it's picking up cans and so on. And so it has a very different approach. Another big difference is that samples are independent from each other in the training data, while for reinforcement learning, previous data influences the data currently being learned from. Say for example, you pick up a can right here, right? And our robot wants to go to the other side of the room and also pick up a can. It might not have enough energy to go to the other side of the room and pick up the can, right? And so picking up the can right here influences whether it's going to pick up the can after that, right? Another important thing is in supervised learning, our model learns to predict a y from an x, and from reinforcement learning, our model learns to maximize the reward. I think technically this isn't fully true. What our model really tries to do is it tries to estimate the best reward that you can take for the current action, and it estimates that landscape. And then we say, okay, just choose the action that has the best reward. We'll get into what all these mean. And so what do we need to set up an RL problem, right? And I'm sorry if I'm going through this a little fast this time. Guess other questions feel free to ask. So what through reinforcement problems, what are some things that we do? This is our state space. Right, so what is our state space? It's basically all possible configurations our model could encounter, right? For example, I don't know if you guys are too familiar. God damn, the marker is never. I don't know if you guys are too familiar with this, but there's this problem called the lunar probe problem. It's like a famous reinforcement learning problem, and you're effectively trying to. You have this lunar probe on the moon, and you're trying to land it, right? And you control the thrust in different directions. And you're trying to get in a specific configuration without crashing, right? And in that case, your action states are what are the things that I can change of the model at a given time? It should be your thrust and so on, right? And your observation, your state states are, okay, where am I? How fast am I going? And so on. Those type of questions, right? It's the current state that you're in, the current state that your lunar model, lunar probe is in, right? And the reward is, okay, am I going in the correct direction? Am I going at the correct speed? Am I going at this correct velocity? And if so, I have some sort of reward, some sort of numerical reward that you're doing the correct, right? An incentive to do the correct thing. And your dynamics is just you have your environment and you have the current action. And given that action, how does that, you go into a new state and what reward you get by going into that new state. And so that is what your state space action piece and void in dynamics. And in the case of, just to give you guys more overreach, in the case of the robot going around trying to pick up these little trends, one possible action space. In this possible action space is, for example, going to the left, going to the right, going back, right? Maybe you have a certain sort of acceleration portion where you try to go faster, go slower, and so on. And then your state space is a current state variable, right? Like, let's say you have a certain battery life. Let's say someone ordered a specific thing and so on. That's the list of information. Then you have your current environment. And then you're just trying to basically maximize the reward in that environment that you're in. Okay, one famous example is AlphaGo. So this was sort of, it revolutionized reinforcement learning, especially around the time that this came out. There's a lot of hype around reinforcement learning because before then there was sort of this sort of minimal a little bit, right? It wasn't reinforcement learning was sort of things like it wasn't as famous as it is now. And in this case, they trained a reinforcement learning model to play the game Go, which is a very complicated game if you guys know how to play it, and it beats the world's best Go play, right? Which is kind of amazing. And in this case, the reward is if you win one, if you lose 0, and the dynamics of just a set of rules and so on. And the action spaces, where to go on the board. Let's say you're playing chess. How do I move my queen? How do I move my king? How do I move my rook? And so on, right? That's your action space. And the state is just literally the state of your board. You just input that into your model probably as a vector. Or if you want to get really spicy about it, you can input the image of your board, right? But you usually just input the board, the vector board. And usually in reinforcement learning, we make an assumption. This assumption, it's important, but it's not something you're going to see every single day. But we do make this assumption that our reinforcement learning problem is a part of this decision process. One of the key properties of the Markov decision process is called the Markov property. Is that given any state, like the future rewards and the reward given that state going for action isn't at all impacted by your previous states. It's not at all. It's independent of your previous state. Right? So you only have to worry about this state and the states afterward. The action that you take in this state to go to another state. So it's independent of the states before it. And so that's like one of the key properties of a Markov decision process. And we sort of make the assumption that reinforcement learning problem is this Markov decision process. So it makes it easier to do and so on. Yeah, this is at the same time the previous state. And so this is sort of like a graphical overview of what a Markov decision process is. Given a certain states, you have an obligation in your environment, you take an action, you go to another state, right? We do the same thing again and again and again and again. That's what a Markov decision process is. And those are just the probabilities of an action. And so what most RL algorithms look like. First, an agent will get some data from the environment. If you're a robot, for example, trying to pick up the environment, get some information from the environment. Where am I? Do I see any cans? What's my battery life? So, right? And then based on this data and the policy the agent has learned, it's going to take another action. So you're going to say, okay, I see a can right there. I have enough battery life. And I think I have enough battery life to go back to the recharging station and just go and get that can, right? So you'll take an action, right? And then based on how the action affects the environment, there will be a reward associated with that, right? And so, for example, if you get a can and if you go back to your recharging station, you get a reward. So there's a benefit, right? And that is your reward. It might also be a negative. Your battery might. So you either don't get a reward or you get a negative. And based on that reward associated with the current action, the agent will update its policy. So it's going to say, okay, I went to that can and I got a negative result, so I won't do it another time, right? So I know that the value, the expected reward for this action is that. So why do it again? You know what I mean? Why repeat that process again? Because you're going to lose. And so how to take an action. And what does it actually mean to take an action? How can we train the model to take the proper action? We'll get into that. And this is where the idea of a Q value comes in. So what a Q value does is it explicitly tells an agent which action should be chosen at which state, based on that Q value score, right? It's like it's basically the expected reward that you get from going from a certain state to another action. Wait, let me draw it to that. That's better. Estimate these key values, what we do have is we have this thing called a Q table, right? So we would have states and actions, right? And for every single state and action, we would have with it associated a Q value, right? And we would go over all the potential actions we can take in the current state. We would say, okay, given this current state, if we take this action, what is the expected reward we can get? We want to maximize that expected reward by taking the action with the highest Q value, right? So we loop through all our potential actions and we just take the one with the highest Q value. And if you guys are wondering what this big equation is right here, what we're effectively saying is we're saying, I think this next slide effectively, sort of like talks about a little bit better. We're saying we have a Q matrix, which at first might be randomly made by some sort of distribution or something. Then we take our Q value, right? And then we update it using this. In this case, we're still thinking about it as a table. So our former Q value is equal to our new Q value is equal to our former Q value plus our learning rate multiplied by the actual reward, right? Plus potential future rewards that we might have if we go to another state. And this discounted factor means that the potential future rewards after this, after taking a certain action for the current state are discounted. So we don't take them into account as much. And we just subtract it from our current Q value. And so that's how we update our new Q value. So all we're saying is we're saying, okay, we took this action because we thought it had a certain Q value, right? But we turned out to be wrong within this range. And based on that metric, we update the Q value so that it reflects the actual Q value of that scenario, of that model, right? Of the environment. And so, yeah. So that's how we update our policy. We just say, okay, we're going to start with some Q value, right? And as we go through our environment and as we, as our model chooses different actions based on some policy, what is the Q value that we have seen? And using those same Q values, we effectively take the difference between our former Q value, actual target Q values, and then we add that to our storage Q values. And so we would do this using a table before, and this is very time consuming and computationally expensive, as you can potentially have a very large state space and a very relatively large action space. And so it'd be very computationally effective to calculate this. And that's where we bring deep Q learning, right? Where rather than have this table, right, of Q values, we just say, okay, we have this model, we give it our state, our observations, right? And it estimates the Q values for a certain action. So your model just literally returns the actions given a state. And we just it returns the Q values given for each action given a state, right? And so we just take the one with the highest Q value and we go on. And if you guys are wondering, right, wouldn't this just be very cyclical? Wouldn't we just take the same actions every single time because we're not, sort of exploring? And that is where exploration comes. We have to have a policy for exploring as well. So in your environment, for example, if you're a robot, you don't want to always take the same path, right? Based on some sort of exploration technique, you want to take new paths. And one way to do this is to take the greedy approach, where you say, okay, we have a probability for exploration, right? We have a probability of just taking the best path we know. If we generate a random number, if that number is within our probability, then take explore a new path. If not, explore the same path. That's how we explore new paths. And the way we calculate our loss in deep networks is we take our target value, we take our current predicted p-value, just take the difference between that, and we use that as our loss. And this has a lot of issues, like it's not very stable and so on. And we'll get into what that means. Yeah, this is basically like a mathematical overview. Sample some action we take it when we update our neural network based on the difference between our target p-value and our p-value.
And we're not actually maximizing. More, we're maximizing over our error in guessing the Q value. And that gives us
Exactly.
the backpropagation.
Exactly.
And we just, as long as we get better at predicting that, predict better.
Exactly. Wait, I hope I'm not butchering that. Wait, that was perfect. Fantastic. Yeah. That's what we're basically sort of like, okay, we have our p-value landscape. Like we want to estimate our p-value landscape better. And so it's like we're in a ship, right? We just want to get to the best p-value, and then we make the illusion that we're maximizing the reward. But instead we're just sort of estimating our Q value better. And in fact, there are actually new models that are coming out. Everyone loves to put transformers on everything. People are saying, let's put transformers all together. Let's call it as well. I forgot the right term, but let's just measure, let's just effectively calculate the causality using that transformer. Let's just give it all our states and observation, and our transformer predicts our action for that specific state. So let's say, for example, you're a robot going in a certain configuration. You say, okay, this is my current state. I want the maximum reward, and the model predicts you an action, right? So the model is sort of exploring the action space rather than the human space. So it's really cool. But yeah, that's a really good point. And open challenges. One thing is training instability. There's a huge issue training this reinforcement learning models. As you can see, there's an issue. One with exploring what type of strategy you would use. And just to be really quick, another thing with the fact that as you're trying to predict your environment, you're also changing your Q values, right? And then your sort of target P values are also changing. And so that creates an instability because you're almost trying to hit a thing that's changing itself. You see, you're trying to hit a target that's changing. So we want to sort of stabilize that. And that's where these things called double Q learning come in, double Q learning networks. They're pretty cool. And you guys want, we can actually talk about that another time or today too, after this. Another big thing is reward specification, where we might have a hard time actually specifying how do we bring the correct reward, right? And what are the bounds of the reward? Because suppose, for example, we want discrete rewards, discrete reward values, right? We only have discrete values given at some interval, right? And suppose you want continuous time interval, like continuous action reward value. How do you choose the two? Which ones are best? And also the correct reward values for the event today. Let's give you guys an example. So this is a game that was trained on an RL model. And if you guys can see, it's circling again and again and again and again and again up in the same location, right? I think, if I'm not mistaken, you remember Sparks, this example?
Yes.
Like, the reason it's doing that is because the model learned a specific set of actions that resulted in a high reward, because the reward settings were
I think what it learned was that,
Yeah, you remember?
And then also, I think it also gets rewarded for going towards the destination, but it doesn't get penalized for moving away. So you just keep going this way, keep going.
Yeah, so as Sparks was saying, like there is an issue with setting up your rewards properly, right? If you set up your rewards improperly, what happens is your model might actually, beat the game, but in an incorrect way. it's like, you failed the mission, but you were successful. Your model was successful, right? So it's like you might have those, you might have that issue. Another thing is exploration, right? So like I said before, your model explores based on some sort of policy. It might be a greedy policy. You might even train a neural network to explore potentially, right? And so on. This in itself is an issue because if you explore too much, right, your model might not learn the best outcomes to take because it's always exploring, right? It's very unstable. The space of all possible exploration is very large, so it might not stabilize. And if it's not exploring, you might learn some suboptimal approach, right? And so what is that balance? And what is the balance between those two? And so yeah, that's reinforcement learning problems, reinforcement learning in general. If you guys have any questions, let me know. I think because just for time, we literally have 15 minutes. So our team. I put some slides on here. I'll just, cover some things. Sure. I'm going to skip through it. Transformers, large language models. These things exist and backbone of a lot of cool stuff. And I think we explained architecture, but we're going to do like more advanced stuff and adding on to it just real quick. So yeah, I'm skipping through a lot of slides. I have a lot of extra slides here. Ignore all this. I deleted these. Oh wait, I need to exit out and they don't exist anymore. Oh, now that they're gone. Okay, yeah. So yeah, BERT, like just a little bit of history of the models that exist and things about them. BERT's a cool one. 2019, Google made transformers. This is used in search and it actually improved search in 2019. It's a transformer encoder. Next, GPTs. You guys probably know these. This is the transformer decoder. And the GPT-2 came out, I think, all like February 2019, same year as BERT. And this was OpenAI, and this was trained to predict next word. Little chart comparing encoder and decoder models and stuff. I think we went over this already last time. GPT-3 came out in June 2020, and the number of parameters, again, that BERT is down there at not even 1 billion parameters, very small. Used it every time you Google search. And then that was GPT-2, which came out in 2019. And then GPT-3 came out in 2020, and that was 175 billion parameters, which is like insane. And OpenAI, what they're really good at is scaling. So they have a lot of money and a lot of GPUs, and they just like train really big models very well. Rough estimates were like $4 million just to train it. So it's like electricity and compute, not even like anything else besides that. And then GPT-2, I think, had 40 gigabytes of data. And then GPT-3, humans couldn't even filter that. So they had 45 terabytes of text. And then they filtered that down to like 500 gigabytes. And then they used that to train the model. And then they did like some fine tuning. Yes.
Did that cost estimate like all the effort that went into like failed runs and stuff? Just the final straight shot?
I think that's fine. Yeah, like I think GPT-4 rough estimates were like 100 million, and then probably like 500 million for total everybody paying the people. Yeah, but like I think GPT-4 people say like around 100 mil or something. Yeah, GPT-3 was measly cool. This is a breakdown of the data set that went into it. You see on Reddit. Common Crawl is just scraping websites, a bot that went and scraped stuff from the internet. What else? It was also pretty cool. I mean, when it first came out, everyone was like, this is crazy, and this is kind of like the big start of all the AI stuff. I had to do my AP Gov assignment. That was funny. But if you used it in 2020, the problem you come in like have a lot is like if you said like explain moon landing, it would like just repeat that a bunch, which is kind of not what you want. And I'll give another example that makes it kind of more clear. If you asked it like, hey, what's the purpose of this code? Like, what does it do? And you give it code, it would like output an A, B, C, or D answer, which like isn't helpful. But you're like, why is it doing that? Well, if you think about it, it's just trained to predict the next word and replicate information from the internet.
And on the internet, if you have a question, then like part of the stuff to help you answer it, most likely it's going to be a test bank, and the answer is going to be like what the text that comes after is an A, B, C, or D, right? So you need to do a process of actually showing it what do you want it to do, right? So this is what we call shots with these models. It's pretty much just examples. We call it like one shot. If we, like, for example, let's say we want to translate English to French, let's say cheese, we want to translate. What we do is we just give it one example. We say like, translate sea otter. We show sea otter is this, I want to say that, and then cheese, and it does way better. If you look at this graph, so this is giving no examples. This is 175 billion parameter model. We put 10% accuracy, but if you give it just 10 to the 0, which is 1, just one example right there, you get almost 50%. And then if you look, they call it few shot. Give a couple more examples. Its performance improves a lot. So literally just giving it like one example of what you want, it improves a lot, and it scales with the models, right? Which means that these large models actually are way smarter. You just have to steer them in the direction you want them to do stuff. So yeah, they're few shot learners. They're not zero shot learners. So how do you make them zero shot learners like ChatGPT? This is pretty much how ChatGPT works today. It's called InstructGPT if you want to look that up. Pretty much it fixes that problem, and this is how you're used to it. I'm not going to go into really how. Here's another example. Look, it does what we're used to. Crazy. They pretty much just get people to write responses, and they fine tune on those responses, but you're actually like following the instruction. And then they also do this, and that leads to better performance. So this is just prompting it, where it just says explain, explain, explain. It's pretty bad, right? Then they do a prompting, which is the few shot we showed, and it does better with larger models. And then they show the supervised fine tuning, which is like train off people writing examples. But we can do even better with this process called RLHF, which is we train a reward model to learn human preferences, and we use that as a signal, train the model further. There's other methods these days like DPO, direct preference optimization, but this is how it was done originally, and that leads to better performance. Yeah, so just quick recap. Okay, and that's the thing. Yeah, and those are some LLMs right now. Oh, Meta is really nice because you know, they're the only ones that actually release the weights, where Google and OpenAI haven't, like Jordan with stability and stuff, more model stuff. Okay, that was just a quick recap. I'm just going over like 1 to 2 little methods that actually in practice we use to like use these models these days. If you want to run it locally, we do something called quantization. So like as you saw, GPT-3 it was really big, and if you look at all the models that are out these days, even the large language models, even Llama, they're pretty massive. Like even the 13 billion parameter model that Llama released, it's up there. But 13 billion, if each parameter is 4 bytes, that's 54 gigabytes. And that needs to be in video RAM. Most like gaming graphics cards are like 8 gigabytes, right? So yeah, we want to somehow compress it, and it costs a lot of money. If you want like a 48 gigabyte card, that's like, I don't know, how much is that? That's like $5,000. And that's to run like one Llama instance. To run, let's say, GPT, which is 175 billion, that'd be like 40K just to run one instance. So that's a lot. Yeah. Quantization, you literally just grab the weights. So our models are made of layers. Layers contain weights. Those weights are floats. And the floats are 32 bits. And quantization literally says, can we compress that float 32 down to a smaller number? So yeah, this is called half precision. This is kind of how NVIDIA actually trains the models. It's called mixed precision. They pretty much just downscale the weights to float 16. But you're like, hey, won't that hurt the model in performance and precision? It will. It does really bad. But they do some smart scaling where there's reasons why. But the main thing is that the gradients are actually very small compared to actual weight values. So what we have to do is when we're doing the gradients and we're storing those, we store those in float 32. But the actual weights we can leave at 16. So we can have lower precision weights, so we can have smaller model files, but in the actual training process, we want the gradients to be precise enough and rich enough. And this is what NVIDIA does. And if you use like NVIDIA GPU speedups, there you go. Not really a performance hit. But what can we go further? So if you have to look on, you got a question? Half the size, yeah. Float 32 to float 16. So it's 32 bits to 16 bits. exactly half size. Yeah. Yeah.
The precision gets much smaller than before. Like we in lack of the lack of precision is a lot greater than a half because it's like exponential.
It's that, yeah. The range is from, instead of from to the negative that, which is like a lot of zeros, to this number, it's from this to 65,000. So it's way smaller, but it actually doesn't hurt it that much. As long as you can train it like that with the gradients, the performance hit isn't actually anything really. It's just the training is hard to do with lower precision. But these networks are very large, so that kind of noise from the precision doesn't actually affect it. Can we go further though? Can we go like int 8, right? This is like 4 times less. And the fact is, like, if you can do, this is int 4 even. But if these tensor cores, these many GPUs, they're actually optimized to run, and they're allowed to run these int 8 or even int 4 operations. So if you can make the model weights that small, it'd be better. But again, what does this show? Yeah, so one method is called LLM int 8. This, I think, is how a lot of Hugging Face models do it. It's changing a lot. I think these are outdated already. Like most of these methods are already. But the problem is there's a lot of, what's this? I'll skip this slide actually. This is a little niche. But what they realize is for large language models, in like the query, like in a lot of the matrices, what they find is a lot of the values are pretty similar to each other, but there's some columns that are actually very away from the mean of the rest of them. So what they realize is what happens if we can actually just separate out those outliers, capture those in a separate representation, and then have the rest of them be in this smaller range, right? Because if you try accounting for all of this in a single int 8 range, like all the values will be compressed on one side, all the values will be compressed on the other. It'd be smarter if you could separate the both and have them both be richer in their own range, right? So that's how LM8 int 8 works. So let's say we have this matrix and we look at this. We can see that these columns right here are actually really big in magnitude, really far away. So what we try to do is try to separate out the values that are really small, and we put them all here and we quantize that down. And then with the outliers, we also do an outlier quantization, right? So we do 2, and we have the outliers actually be a higher precision. This is just something we noticed in models. So like, wait, let's have this kind of property in them. It'd be smart for us to quantize in this way, where we have low precision, the things that are around 0 or whatever, and then these ones that are very high variance of very large magnitude, we do different. And then at the end, we just do the math with those. Any questions? These are just a bunch of quantization techniques. There's other ways to do this. There's different kinds of ways you can do it. You can just train the model, then cut the weights down and quantize them. That normally hurts it. So there's other methods where that's the method here. You just pretty much train the model, quantize it, cut it in half, or lower the precision. And again, this is a very naive way of doing it. You just get, you just find the mean and you divide it by it, and then like you normalize it pretty much into the range of like int 8. And again, int 8, by the way, is like the integers, negative 127 to 127. So that's like not that many values. It's 256 values, but it actually only shows like a very minimal percent hit, like 2 to 5%. Like it's not actually that bad, and you're quantizing it like 4 times the size, which is very, very good for memory footprint and all that stuff. Better quantization techniques. Can we do better? So quantization aware training. This is where you actually kind of like mixed precision, where you're aware that, hey, I'm actually going to be using this lower precision values. So in the forward pass, you use the lower precision so the model can learn to account for you not being as accurate and noisy. Because when you train the initial model, it might be using that precision to do some computation and be smart about stuff. But what you do here is you just train the model to, like in the forward pass, account for the fact that its weights are going to be really small, maybe even int 8. And that this allows it to compensate more for the noise that, or the loss it's going to have from having smaller weights. And again, yeah, there's more stuff there. But again, these are just methods to compress your models more. And this is a chart of like the main methods out there. GGML is really good, I think, for like inference on CPU. This is how like the Llama CPP repo I think uses, and that's you can run it on like your laptops even. Different methods. There's a lot of quantization methods to make it so it's optimized on the hardware, and that means like I can even run like a Llama 13 billion or even 30 billion like just on my laptop without even needing a GPU, which is pretty crazy. So yeah, that's quantization. That's a cool technique, compression model. I'm just gonna talk about one more, and then I think we can go. This is called LoRa. It's kind of cool. So let's say you have a big model like GPT. It's 175 billion parameters. It's super massive. If you want to fine tune it, you're gonna have to move and train all of those weights. That means storing the entire model, like we said, maybe you quantize it, but then you also need to store the gradients of those, which is like another copy. And again, those copies, like we said, need to be pretty rich as well. So it might be even a bigger copy than the quantized model. So this is a lot of weights to train to fine tune the model. Let's say the model writes an essay, you want to have it like you have GPT, you now want it to fine tune it to write like poems or something. Or you have like an image generator model, you want it to like generate only portraits or something, right? Like you don't want them train this entire large model. So this idea of adapters were the previous work. We pretty much just inject feed-forward layers inside every single block of the model. And you freeze the rest of the weights. The rest of the weights don't change, but you have these little adapters that learn how to modify and adapt the model generation so that it slightly tweaks it and moves it in their direction. So the only thing you're training in this part is these little adapter modules you've added, right? And this makes it so the amount of weights you have to train is way, way less. The amount of gradients you have to store is way, way less. And it's just like less weights to train and actually trainable if you have less compute and things like that. Yeah, so if you look at this, this is them fine tuning the entire model. That's how many parameters they need. That's 175 billion, right? And then these are a bunch of adapter methods. And adapters, they only use here like 40 million parameters. If you actually look at their accuracy, it's even better, even. And that's because if you think about it, you kind of don't need to move all the weights to fine tune it to generate. You just need to adapt it a little bit. And maybe moving all the weights is maybe hurting you. So you can use way, way, way less trainable weights, and it can achieve equal to or even better performance. So it's just smarter to use these adapters. But a smarter technique came out called low rank adaptation for large language models. It's pretty much called LoRa. The idea is that, well, real fast, let's do a problem with adapters. A problem with adapters is that this actually slows down inference time a bit. That's the one thing they don't show here and they don't really mention, is because you have to wait for another layering process. So you're adding a bit of inference time. So this new technique, LoRa, it actually does the same performance, less weights, and it doesn't require, it doesn't slow down inference time. So how does this work? The idea is we have these large matrices in our models. And the question is, wait, what happens if we could decompose these into two smaller matrices? And this is called low rank decomposition. So like imagine this matrix is like 100 by 100, that's like 10,000 values, right? But we can maybe decompose that into 100 by like 2 matrix and a 2 by 100. When you multiply those two, you do your matrix back, that's 100 by 100. It gets you back to 100 by 100. But this in total would be 100 times 2, plus 2 times 100, that'd be 400 values. So it's 400 values compared to 10,000 values, which is way less. And this is the main idea behind LoRa. What you do is you have your weights. And what you do is you have it inside, you have a difference in weights. You're not modifying and changing the original weights to fine tune. You're storing a difference. And if you just stored this normal difference, this would just be the same as fine tuning the original. Like let's say this is 175 billion parameters, the difference would also be 175 billion parameters. It's not saving you anything. But what we do is we decompose that difference into that low rank decomposition. So again, if this was like 100 by 100 matrix, this would be, and then we go to 100 by 2 and 2 by 100. Now you're having 400 values compared to 10,000 values. So what we're doing is we're storing the difference matrix as a low rank decomposition. And surprisingly, this is like 10,000 times less memory to train. Like we showed the adapters. This is what we showed before, right? These are the adapters. And they can use even less and get similar performance to the rest of these. It doesn't slow down inference time. And it actually gets higher or equal to accuracy, which is crazy. And you're like, wait, how is this even possible? I thought it'd go, like, again, like the adapters. You'd think that adapters, since they have less trainable parameters, they'd perform worse. But if you actually look, they go into it a bit. Here are more results. So by the way, these ranks are extremely low, like insanely low. Like they can go down to rank 2. Like these matrices were, I forgot the hidden dimension for GPT is like over 10,000 by 10,000 maybe, because you have, it's very, very high. But the whole point is that we're decomposing a really large matrix into like a 10,000 by like 2 and a 2 by 10,000. Like that is insane. But it actually doesn't really hurt performance. You can do an 8 by like 10,000 or 2 by 10,000, and it actually performs pretty well. And you're like, why is this? How is it so good that we can really decompose these matrices really small? They kind of went into it. It's kind of cool. The fact is, like, the intuition, I think, is that when you're fine tuning, the model already knows how to generate like faces or something. You just need to push it in that direction. You don't need to be moving all the weights to tell it how to generate a new image. You're actually just saying, amplify this direction in your generation space. And same thing with large language models. It already knows how to write a poem. You just want to make it better at doing that property. So again, this idea of pre-training, these models already have this large implicit knowledge. We just need to push them in that direction. And what they found is actually in the subspaces, in the low rank, like what rank does it find? It's actually just amplifying. This is not the page. Next page is it, I think. Yeah. So they compare the original weights to the change in weights. And the change in weights, all they're actually doing is just amplifying directions that are not emphasized in the original W. And that's the reason why. You don't need to modify like all the entire subspace of the weights. You only need to, in a couple directions, amplify those weights. And that's what the low rate matrix decomposition does. It only lets you have 2 degrees of freedom in the weight change dimension. Whereas when you're fine-tuning the entire model, you're having to let it learn, like you let it control all the entire subspace and move it around. And that might actually hurt it because it's too complicated for it to understand. So LoRa is not only a small file you have to add to do fine-tuning of a model. It uses less weights, doesn't have inference penalty, and it actually trains better and faster. So yeah, it's a better technique. Yeah, question.
So you're allowing Delta W to update all the weights, but it's only like picking a subset of its amplify.
Yeah, it's picking a subspace of the weights to amplify, right? So instead of, like, again, we can have a delta, right? Like literally, like imagine it's a 100 by 100 matrix, right? We have a delta of how much we want to change those. When we actually do the full computation, we just add them, right? Or subtract them, right? But what we say is that delta isn't, that matrix isn't, you're not allowed to control every single value in here. You're only allowed to control these 2 matrices, which multiply get you that. And if you think about it from a linear algebra perspective, there's no way for that matrix to have more than rank 2 if it came from a 100 by 2 and a 2 by 100 matrix, right? Yeah. So that means that matrix, its actual subspace, degrees of freedom it can exist in, is only 2-dimensional, right? So it's picking a subspace of this 100 by 100 space, this 100 dimensional space. Yeah. So we're saying in this weight, like imagine this weight matrix or these weight matrices represent some kind of like, generation or how I'm supposed to generate an image or generate the next word or like how I'm supposed to do something. This is only allowing you to move in a certain vector direction in that space. Not, yeah, like amplify only a certain direction vector in that space.
Okay, because it's the subspace corresponding to this order.
Yeah, it's a subspace of the weight matrix, right? We're not letting it control the entire weight matrix to say, you can do whatever you want in here. You can mess up all the weights, change them however you want to make it so you're better at poems. No, we're like, you can only control 2. Pick the 2 that you find the most important to do the task you want. And that's better. We don't actually giving it more freedom to do all the weights is way more complicated. It costs more for us. It's a lot more to train, right? And it's actually smarter to give it less freedom to do it. And it can only control 2 ranks of our matrix to change, right? Yeah.
Yeah.
So yes.
Any other questions?
No? Okay. That's it. So that's like two modern techniques. Yeah, it's way better. Yeah, like 10,000 times better. It's just better. It's literally LoRa's just better. I think I have Jordan's slide somewhere. The subspaces is kind of cool. They went into the math and explained like how the similarity and stuff like that does. So like let's say you again have an image generation thing. You can just, if you want to fine tune it to like generate portraits of somebody, you just, instead of sending over an entire fine tuned 5 GB stable diffusion model over to someone, here's the one for portraits, here's the one for like cartoon, like, you know what I mean? You just send them like a 5, like 30 megabyte like file, which is that LoRa decomposed difference file. And then now you just put it as like a adapter, but it's a LoRa, right? Next to it. And now this model can do faces. And you know, I want to get another adapter for the stable diffusion model. I want it to like generate cartoons, and you just put that file on the side. And then again, that 30 megabyte file can expand to a really big one, like when you reverse the decomposition. But the actual weights you have to store are very small. It's a subspace of the original delta. Yeah.
So if you think about this in the latent space again, so what LoRa is doing is picking like a portion of the latent space. So if it was like you can pick like the subspace that corresponds to the digit 1 and then amplifies that.
Yeah, kind of, yes, but it's like an aggregate because I mean, one matrix doesn't control the one generation, right? It's pushing all of them in the direction that they mean to help in generating ones. But yeah, generally kind of, yeah. Like, because there's multiple weight matrices, not a single one, right? So like each one, it's telling each one to contribute more to the direction of ones. Yeah. So that's LoRa. Yeah, QLoRa, that's a thing. You can quantize and you can do this LoRa. So you can have the model quantize while you're doing it. And this is actually how a lot of open source training is done. Yeah. I'll just quickly say this is a thing and then I'm not going to explain it. There's cool papers on, we've explained attention before, but there's a lot of papers that pretty much claim that you can replace the self-attention mechanism. This is another cool thing. But I'm not sure I have too much time to explain it. But yeah, you pretty much have this self-attention. You have vision transformers, raw transformers, but they realize why don't you just replace that attention mechanism with some other kind of algorithm that just mixes everything together and actually achieves pretty good performance, or even like with faster inference. And then even for things like language, they replace the entire self-attention mechanism with a Fourier transform, which just combines them based off where they are relative vision-wise. And that actually achieves, I think, 92 to 97% of accuracy upper, which is the original model, right? The Google one that helped them search, which is very impressive. Again, the transformer paper, attention, all you need, we thought self-attention was a related thing, but we're realizing we just need a different mixing mechanism to do that. And last thing, structured state space models. These are like new. This is a new thing. The paper was actually rejected, which is kind of crazy. This paper, yeah, it's called Mamba. It was rejected. I mean, like Word2Vec was also rejected, and that was an amazing paper, right? But this is also another structure that can replace the self-attention mechanism, and a lot of people are like kind of raving over it. And it's really, really cool and good. And people are like, this is the new kind of thing right now.
It's paper that has been rejected. It's Transpost paper. It's the architecture behind OpenAI's extremely good video generation model. When that was first submitted to CVPR 2023, it was rejected because there was not enough novelty. So yeah.
Yeah, there's really good papers that get rejected, but they have like immense impact.
Yeah. Anyway, so you've just seen there, 4 big topics of 4 of not the moment I won, but our team also gave a full actual reading group on this. Back in the days, the beginning of this quarter. You can view it on our channel as well. But yeah, that is. Oh, that's him. Oh, hi. I know, crazy. Anyway, so that is the end of workshops tracks. Workshops actually. I'm really thankful that all of y'all stuck with us to the end with this. And next quarter, instead of we're gonna come next week, is going to be project track. Again, the applications for projects should open somewhere end of this quarter or beginning of next quarter. And because you have done both apply track, I'm assuming, and also theory track, you are basically guaranteed a spot. Actually, you are guaranteed a spot since you have also done theory track. So yeah, thanks for coming. That was one wild quarter, and I hope to see you next week at the symposium. Please RSVP and also show up if you want. Yeah, thanks for coming.